the most difficult subjects for high school students is mathematics. Students often view the content as disconnected from their lives, they find application problems as complex, and the multiple ways of approaching problems often confuses them. Systems of equations are problems that require students to find the intersection of two linear equations. These problems are rarely applicable to real-world situations, and the various methods of solving the equations often leave students confused about which to choose. When teaching systems of equations over the summer to a group of students, I came into contact with such student misunderstanding and frustration. I instructed the students from a more traditional methodology. I scaffolded the students, yet I did not provide hints, feedback, and catch student errors as they arose. Students were not encouraged to verbalize their understanding, and while the lesson gained complexity, the content was not situated in real-world scenarios. This traditional approach was not as effective as I had hoped. The average on the summative assessment was only a 70%. Also, through a survey, the students indicated that the material was not conveyed as effectively as possible, and that it did not represent real-world problems. Hoping to have a better experience with systems of equations, I decided to implement an integrated instructional approach entitled Cognitive Apprenticeship. Collins, Brown, and Horam stress that conceptual and problem-solving knowledge acquired in school remains largely inert for many students. When students encounter problems that fall outside the standard textbook problems, they are at a loss for what to do. Cognitive apprenticeship is an integrated approach which addresses this problem. 4 of the many pillars of cognitive apprenticeship are: 1. To scaffold students beginning with think-aloud modeling and transitioning to coaching. 2. To encourage students to cooperatively articulate aspects of problem solving and to reflect upon how their approach compares to a given model. 3. To increase the difficulty and diversity of problems so that students become accustomed to adapting their methods. And 4. To implement real-world problems that require students to compare various avenues of solving. I began the lesson by modeling 2 diverse approaches to solve a systems of equations problem. I structured this model to demonstrate the basics of systems of equations prior to exposing students to more complex and diverse problems. Additionally, I hope to initiate a community of practice by demonstrating multiple approaches to solving a problem. As I began the overarching process of scaffolding, I also made sure to think aloud and demonstrate the importance of considering my options for a problem. I'm trying to solve this systems of equations, which is basically where 2 lines intersect. These 2 lines look simple enough to graph. I could use the slope and y-intercept if I wanted to find the intersection of these 2 lines. I also need to consider if the answer might be a decimal, or if the numbers are very large, I may not want to graph this. In that case, I could substitute -1 plus 2x in for y in the other equation. Then I'd have all x's, and I could solve for x, and then go back and substitute for y. After modeling a few examples, I encouraged the students to articulate their knowledge by explaining the 2 methods I modeled.
Since system of equation is just 2 lines, you can graph the 2 lines and use the slope to find their intersect. But if the answer is a decimal, you may need to use the substitution method. You will solve for one variable in one equation and substitute in for the other equation.
After the students articulated their understanding, it was time to coach the students. The first problem that the students faced was a more complex problem, similar to a problem from a recent standardized test. Given that the students were unsure how to set up the problem, I provided hints. The students also came to the realization that one of the linear equations would need to be placed in slope-intercept form, thus demonstrating their ability to handle problems that deviated from the model. Using the smartboard, the students successfully found the solution. I continued to coach the students through more complex and diverse problems, yet with less support. The next problem was a quintessential example of situated learning. The problem was an application problem that related to gym membership. I assisted the students in setting up the equations. From there on, the students chose one of the 2 approaches and correctly solved the problem. The students reflected upon their understanding of the problem and its variance from their model.
This problem was different from the model because the equations needed to be creation from the situation. You needed to understand what a constant and coefficient were.
As the scaffolding progressed, there was less and less coaching needed, and the problems became more complex. One of the final situated problems that the students solved revolved around the school dance. The students almost entirely set up the equations independently. This problem truly created a community of practice as the students challenged each other on the different ways in which to solve.
The numbers are too large to graph, but we need to solve for one variable. We should solve for A in the second equation.
No, we should not solve for a variable in the first equation.
The students eventually chose to isolate the variable in the first equation. However, it appeared as if they had begun to reflect and articulate more effectively in cooperation with one another. After the lesson, I assessed the students using the same summative assessment that I gave to my students over the summer. Their average score was 23% higher, and their opinions seemed to be more in favor of my instruction and of the applicability of the lesson. It appears as if Cognitive Apprenticeship successfully scaffolded students through articulation and situated learning.